this video, we're covering one of the most important ideas in calculus, the fundamental theorem of calculus. You'll learn how it connects derivatives and integrals and how it lets us evaluate definite integrals efficiently. This theorem is presented in two parts. Part 1 explains how the derivative of an integral gives back the original function, and Part 2 shows us how to find exact areas using antiderivatives. We'll work through clear, step-by-step examples so you can see exactly how to apply both parts of the theorem. Be sure to download the free guided notes to follow along, highlight the theorems, and work through each example with me. Let's begin by looking at how the fundamental theorem of calculus connects the two main ideas in calculus, differentiation and integration. Differentiation is the study of rates of change, in particular, how fast something is changing at a specific moment. For example, a car's speedometer shows the instantaneous speed, which is the derivative of the distance function. Integration, on the other hand, is the study of total accumulation, meaning the overall amount of change over an interval. If differentiation tells us the speed at any moment, integration tells us how much total distance a car has traveled. The fundamental theorem of calculus acts as a bridge between these two concepts, showing that differentiation and integration are inverse operations. It's what allows us to compute definite integrals efficiently without having to approximate area using Riemann sums. We're now going to learn about the fundamental theorem of calculus, part 1. This theorem provides a formal statement of the inverse relationship between differentiation and integration. It's one of the most beautiful ideas in calculus and tells us how accumulation and rate of change are connected. Let's begin by looking at the accumulation function. G of x in our diagram represents the area under the curve y is equal to f of t, starting at a fixed point a, there's a, up to a variable point x, which is right here. G of x is the definite integral from a to x of f of t dt, and it's also called the area so far function. It tells you how much total area, distance, volume, or any other quantity has accumulated up to that point. Now that we understand that g of x is the accumulated area, the next question that we need to answer is how fast is this accumulated area g of x increasing as x increases? As x increases by a small amount, the accumulated area is also increasing by a small amount, and this amount is shown here in pink. This new area is equal to f of x times dx. That's just the height times the width. To find how fast this accumulated area g of x is increasing as x increases, we need to look at the rate of change of the area g of x. That rate of change is equal to the derivative of g of x, and it's equal to the new area divided by dx. Up above, we saw that the new area was f of x times dx. We now divide that by dx, and we get that it's equal to f evaluated at x. So the rate of change of the area g of x is just f of x. The accumulation function g of x is an antiderivative of f of x because its rate of change equals f of x. The fundamental theorem of calculus, part 1, formalizes this connection between accumulation and rate of change, and it shows us how derivatives and integrals are related. Let's now see what this theorem tells us. The Fundamental Theorem of Calculus Part 1 tells us if f is continuous on the closed interval from a to b, then the function g is defined as g of x is the integral from a to x of f of t dt, where x ranges between a and b. G of x is continuous on the closed interval from a to b, just like f was, and it is differentiable on the open interval from a to b. And the most important part is that the derivative of g of x is equal to f of x. I've summarized this down here in our blue box. If g of x is the definite integral from a to x of f of t dt, then g prime of x is just f of x. Let me say this a little bit more simply. The derivative of a definite integral with respect to its upper limit, which in this case is x, equals the value of the integrand, that's f of t, evaluated at that upper limit, which is x. We're going to walk through an example where we are going to find the accumulated area under a function. We're going to let g of x equal the integral from a to x of f of t dt, where f is the function whose graph is shown. Down here we can see what f of t looks like. We are going to find the accumulated area by evaluating g of x for the values x is equal to 1, 3, and 6. This example illustrates how g of x represents the accumulated area under our function f of t from 0 to any point x. I'm going to go ahead and recopy what g of x is. Let's put it right over here. G of x is the integral from a to x of f of t dt. If we look up at our graph of f of t, we can see that t starts at 0, so that tells us that a is equal to 0, and we're going to find g of 1, g of 3, and g of 6. Let's start by finding g at 1. All we have to do is we have to replace x with 1. So this is the integral from 0 to 1 of f of t dt. If we look up at our graph, the integral from 0 to 1 of f of t dt is this area right here. It is a triangle, so we can write our answer as 1/2 the base times the height. Let's see what that is. This is 1/2, our base is 1, and our height is 1, so we get the value 1/2. So g of 1 is equal to 1/2. Now let's find g at 3. This is the integral from 0 to 3 of f of t dt. Because we already know what the integral from 0 to 1 is equal to, we're going to split this integral up into the integral from 0 to 1 of f of t dt plus the integral from 1 to 3 of f of t dt. That way we don't have to do double the work. This integral we already found to be equal to 1/2, and then this integral is this area right here up on our graph, and because it lies below the x-axis, it is going to be equal to minus 1/2 its base times its height. Let's see what that is. G of 3 is then 1/2 minus 1/2. Pull this graph back down. Our base is 2 and our height is 1. So this is minus 1/2 times 2 times 1. And this gives us 1/2 minus 1, which is equal to minus 1/2. Let's go back up here at our graph because I want to show you something. Notice that in our graph, as we go from x is 0 to x is 3, there is more area under the x-axis than there is above the x-axis, which is why our answer is negative. Now let's find g at 6. This is the integral from 0 to 6 of f of t dt. Because we know the integral now from 0 to 3, we're going to split this integral up, and we're going to integrate from 0 to 3, f of t dt. And then we're going to add on the integral from 3 to 6 of f of t dt. The integral from 0 to 3 is equal to minus 1/2. Now we need to find this integral. Let's go back up and look at our graph. That integral is the area under this triangle right here. And this triangle has a base of 3 and a height of 3. So this part is going to be 1/2 base times height, and this is 1/2 3 times 3. Let's see what this gives us. We have minus 1/2 from our first integral, and then we have 1/2 times 3, which is 9. So this is 9 minus 1 over 2, which is 8 over 2, and this gives us a value of 4. This tells us that the accumulated area from 0 to 6 is equal to 4. It makes sense that our answer is positive because if you look at the red triangles, you can see that there is more area above the x-axis than there is below the x-axis. We're now going to walk through some examples where we're going to use part 1 of the Fundamental Theorem of Calculus to find the derivative of the given function. Just to make things easier, I have written down the essence of the Fundamental Theorem of Calculus here in this green box. The Fundamental Theorem of Calculus tells us that if g of x is the integral from a to x of f of t dt, then dg dx, or g prime of x, is equal to f of x. Let's now look at our first example. We want to find g prime of x, and the Fundamental Theorem of Calculus tells us that the derivative of g of x with respect to the upper limit x is the integrand, which is the quantity 2 plus t to the 4th raised to the 5th power, evaluated at the upper limit x. So this is just 2 plus x to the 4th raised to the 5th. And we'll go ahead and highlight that. Now let's look at our second example. Notice in this example that the variable x is in the lower limit. To use the Fundamental Theorem of Calculus, the variable needs to be in the upper limit. So we are going to start by changing the limits of integration and writing g of x as minus the integral from 4 to x t squared sine t dt. Remember that when you switch the limits of integration, all you do is multiply by a negative. Now we can go ahead and find the derivative of g of x by using the Fundamental Theorem of Calculus. We have g prime of x is equal to the integrand t squared sine t evaluated at our upper limit x. So we have our negative, and now we're going to have x squared sine x. And there's our answer. Let's now look at example 3. This example is different than the first two because in the upper limit, we have 1 minus 3x. So it is not a single variable. we can only use the Fundamental Theorem of Calculus Part 1 to find a derivative if we have a single variable in the upper limit of integration. So what we're going to do is we're going to let u be equal to 1 minus 3x. So g of x is now g of u of x. The integral from 1 to u of t cubed, all divided by 1 plus t squared dt. If you're thinking, I think I've done something like this before, think about the chain rule. That's exactly what we're going to use to find the derivative. The chain rule tells us that dg dx, when g is a function of u, which is a function of x, is equal to dg du times du dx. Let's see what this gives us. Let's look at dg du first. That is just the derivative of this function right here with respect to u. And now u is our upper limit of integration. So dg du is just this integrand evaluated at u. So this gives us u cubed, all divided by 1 plus u squared. Now we have to think about du dx. U is given right here. So du dx is just the derivative with respect to x of 1 minus 3x. This gives us u cubed all over 1 plus u squared times this derivative, which is equal to minus 3. Now, we're not quite done. We need to put our answer back in terms of x. So we're going to use this value of u and plug it into our answer. This gives us the quantity 1 minus 3x cubed, all divided by 1 plus 1 minus 3x quantity squared times minus 3. And let's rewrite this as minus 3 times 1 minus 3x quantity cubed, all divided by 1 plus 1 minus 3x quantity squared. And there's our final answer. I think this problem was the hardest one, so you may want to go back and see if you can work this one on your own. We're now going to learn all about the Fundamental Theorem of Calculus Part 2. The Fundamental Theorem of Calculus Part 2 provides a direct method for evaluating a definite integral using antiderivatives. This is going to be a lot easier than having to use Riemann sums. Let me just remind you what the Fundamental Theorem of Calculus Part 1 tells us. It tells us that if we have a function g of x, which is the definite integral from a to x of f of t dt, then dg dx, or g prime of x, that's just the derivative of g, is equal to f of x, which is the integrand evaluated at the upper limit of integration. Since g prime of x is equal to f of x, we can say that g of x is an antiderivative of f of x. To get to the Fundamental Theorem of Calculus Part 2, we have to complicate this a little bit, and we're going to let a function capital F of x be any antiderivative of little f of x. And what we're going to do is we're going to compare this to g of x. Since any two antiderivatives differ by a constant c, we can say that capital F of x minus g of x is equal to a constant c. We can then rearrange terms and say that capital F of x is g of x plus c. I'm going to put a red check here because we're going to come back to this a couple of times. What we're going to do now is we're going to see how we can use the expression that I marked with a red check and the definition of g of x in the green box above, right here, to find a formula for the definite integral of f of t from x is a to x is b. So our goal is to find a formula for our definite integral, and that way we won't have to keep using Riemann sums. How we're going to do this is we're first going to let x be equal to a. This gives us that capital F of a is equal to g of a plus c. We're just substituting in that x is equal to a. This function here comes from our green box up above, and that's what g of x is equal to. Now we're going to let x be equal to a, and notice that a is now in our upper limit, and we're integrating from a to a, so that integral is equal to 0. And we can say that f of a is equal to c. Let's put that in our pocket for a minute, and we're going to come back to it. Now what we're going to do is we are going to let x be equal to b. So let's come up here to the right, and we let x be equal to b, and we get capital F of b is g of b plus c. Now, we know what c is, and we can substitute in that c is capital F of a. Now what we're going to do is look at this formula for our integral, and we're going to let x be equal to b. And that gives us that g of b is the integral from a to b of f of t dt. Hang with me, we are almost done. What we're going to do is we're going to take this expression and put it up into that equation. This gives us capital F of b is the integral from a to b of f of t dt plus capital F of a. Now all we have to do is just switch around terms. We'll pull the capital F of a to the left, switch the sides, and we end up with the integral from a to b of f of t dt is equal to capital F of b minus capital F of a. And that's exactly what the Fundamental Theorem of Calculus Part 2 is. The Fundamental Theorem of Calculus Part 2 tells us that if f is continuous on the closed interval from a to b, that's super important. The theorem does not apply if f isn't continuous on that interval. Then the integral from a to b of f of t dt is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. In other words, it's a function such that the derivative of capital F is equal to little f. I'm going to now say this in a way that makes it easier when you go to use this theorem. Our theorem tells us that the definite integral of a function equals the antiderivative of that function evaluated at the upper limit minus the antiderivative evaluated at the lower limit. And that's all there is to it. Let's now walk through some examples where we are going to use the Fundamental Theorem of Calculus Part 2 to evaluate definite integrals. I'm going to start by reminding you what the Fundamental Theorem of Calculus Part 2 is. It tells us that if a function little f is continuous on the closed interval from a to b, then the integral from a to b of little f of t dt is capital F evaluated at b minus capital F evaluated at a, where capital F is the antiderivative of little f. Let's look at our first example. We are going to evaluate the given integral. In part A, we have the integral from 1 to 3 of x squared minus x plus 4 dx. The Fundamental Theorem of Calculus Part 2 tells us that this definite integral is equal to the antiderivative of each term in our integrand evaluated from 1 to 3. The antiderivative of x squared is x cubed over 3 minus x squared divided by 2 plus 4x. And we're going to evaluate this from x is equal to 1 to 3. What we do first is we let x be equal to 3. So this is 3 cubed over 3 minus 3 squared over 2 plus 4 times 3 minus doing the same thing, but letting now x be equal to 1. So this is 1 over 3 minus 1 over 2 plus 4 times 1. The biggest mistake I see students make when doing this is to not distribute this negative to all three terms. That's why I like to write it like this first, because it helps to not forget that. Let's see what we have now. 3 cubed divided by 3 is just 3 squared, which is 9. And then we have minus 9 over 2. We have a plus 12. And then we subtract off 1/3. And then we have minus a minus 1/2. So this is plus 1/2. And then minus 4. Let's add our constants first. 9 plus 12 minus 4. That is 5 plus 12, so that gives us 17. And then we have minus 9/2 plus 1/2. That gives us minus 8 over 2. And then we have minus 1/3. Minus 8 over 2 is just 4. So 17 minus 4 is 13. And then we have minus 1/3. Let's get a common denominator of 3. 3 times 13 is 39, so we have 39 minus 1. And this gives us a value of 38 divided by 3. And there's our answer. Remember that a definite integral is always equal to a number. Let's now look at part B. We are going to evaluate the integral from 3 to 9 of dx divided by x. This is the integral from 3 to 9 of 1 over x dx. And you just have to have memorized that the integral of 1 over x is the natural log of the absolute value of x, and we're going to evaluate that from 3 to 9. Since 3 and 9 are positive, we can drop the absolute value, and this is just equal to the natural log of 9 minus the natural log of 3. We can simplify this by remembering that the natural log of a minus the natural log of b is equal to the natural log of a divided by b. So this becomes the natural log of 9 divided by 3, which gives us an answer of natural log 3. Now let's look at part C. In part C, we have the integral from pi over 3 to pi of sine theta d theta. This is going to be the antiderivative of sine theta, which is minus cosine theta. And we're going to evaluate this from pi over 3 to pi. This gives us minus cosine of pi minus cosine of pi over 3. You just have to be careful with negative signs there. The cosine of pi is equal to minus 1. So we have minus 1. And then our two negatives becomes a positive. And cosine of pi over 3, that is equal to 1/2. I always remember this by thinking that pi over 3 is 60 degrees, and cosine is the horizontal component of the triangle, and it's smaller, so it has to be 1/2 instead of root 3 over 2. This gives us an answer of 1 plus 1/2, which is equal to 3/2. Now we have one last example. I wanted to include this because this trips students up all the time, and it is so easy to do this calculation wrong. We're asked to find out what is wrong with the following calculation. Let's walk through this. If we have the integral from -1 to 2 of 1 over x squared dx, this is just the integral from -1 to 2 of x to the -2 dx. We can then write down the antiderivative. We're going to add 1 and subtract by what we get. And we're going to evaluate this from -1 to 2. So that's exactly what that middle step showed. This then is -1 over x from -1 to 2. This is -1 over 2 minus a -1 over -1. And this gives us a -1/2 minus 1, which is -3/2. So we got an answer exactly like they did. So now we have to think about what's wrong with what we did. Well, we can think about this in two ways. Notice that our answer is less than 0. Let's think about this. If we look back at the function that we are integrating, it is 1 over x squared. 1 over x squared is greater than 0. So the area under this curve should be positive. But it's not. We got that it was negative. So that tells us that we're definitely doing something wrong. What we have to do is go back to the conditions on the fundamental theorem of calculus. Let's go back up at the top and let's look at this. Our condition told us that f has to be continuous on the closed interval in order for us to use this theorem. Notice down here with our function that it is undefined when x is equal to 0. And 0 is in the interval from -1 to 2. So we can't use the fundamental theorem of calculus to evaluate this integral. And that's why our answer is wrong. If you plan on continuing on and studying Calculus 2, you'll see how to evaluate integrals just like this. And that's it. You've learned both parts of the fundamental theorem of calculus and practice using them to evaluate definite integrals and connect derivatives to areas under a curve. To really master this theorem, make sure to review the theory and work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.